Hello everyone, I am Dr. Peeyush Kumar Kamlesh, Associate Professor at Poornima University, Jaipur. I am here going to present a title, First Principles Investigation of Physical Properties of Lead-Free Halide Double Perovskites. So this is the list of contents. Now the perovskites are materials with the general formula ABX3, where A and B are cations and X is an anion. Based on composition, they can be classified in two types, oxide perovskites and halide perovskites. So halide perovskites have one of the examples CsPbBr3, which exhibit excellent optoelectronic properties but face lead toxicity issue. So to get rid of this lead toxicity, we study double perovskites and we replace lead with less toxic cations like silver, bismuth, or antimony to enhance stability and eco-friendliness. One of the examples is CS2AgSbBr6. It is a promising candidate due to its significant band gap, stability, and lead-free nature. So we found some research gap. Limited studies exist on its combined structural, optical, and thermoelectric electric characteristics using first principles analysis. So in the present work, we are focused to study the structural, electronic, optical, and thermoelectric properties of this halide double perovskite material. So we used Win2K simulation code to carry out our studies. Exchange correlation effects were treated using PBE functional under GGA. Structural optimization performed using full potential linearized augmented plane wave method. Electronic, optical, and thermoelectric properties computed after optimization. And the Monaghan's equation of state was used to extract bulk modulus and at equilibrium volume, right? So the calculations we have done like this, and the thermoelectric properties were computed up to 900 Kelvin using bootstrap simulation tool. And this graph you are seeing here is the volume optimization curve, which is plotted between energy and the volume. So for multiple steps of the volume, we just increase in steps of 5 and decrease in steps of 5% volume, and then we calculate the energy. Then we found that the point which is at the bottom of this curve, for this point we have the minimum energy. It shows that the structure corresponding to this point is the most stable structure. So we extract the parameters from this curve. This material crystallizes in cubic structure with a space group Fm3m, and the arrangement of CS, Ag, Sb and Br ions demonstrate corner sharing octahedral geometry, which you have seen in the earlier figure. So after volume optimization by least square curve fitting of Monaghan's equation of state, we get the optimized lattice constant is 10.955 angstrom. Bulk modulus is 33.887 gigapascal. The calculated structural parameters are in the good agreement with the other theoretical results. This is the band structure. It shows the indirect band gap of 1.567 electron volt for this material, and these are the density of states curves. The lower curve is showing the density of states in a small range of energy, and by this we see that the major contribution in this material in the density of states comes from the Sb atom, okay, and that too from the s orbital of Sb atom, okay. So the indirect band gap is 1.567, shows slight variation with the other theoretical results, maybe due to different exchange correlation potential functional or simulation tool. The previous calculation have been computed using other simulation tools like Quantum Espresso and WASP, and in those tools they use pseudo potentials. Here we have used the full potential method, so there is a little variation in the band gap we found here. So valence band is dominated by AgD, SBS and BrP orbitals. Conduction band is mainly dominated by SB p orbitals. As you can see in the top right corners graph. Okay, so materials is suitable for optoelectronic application. This is the curve for optical properties. You can see here there are 8 optical parameters we have shown in this curve. So dielectric function in figure A, it represented as epsilon 1 omega, is associated to electronic polarization and anomalous dispersion, while epsilon 2 omega is shown in figure B is associated to optical absorption in the compound. Epsilon omega and refractive index n omega show strong peaks in the visible region. As you can see, the peaks are between 2 to 3 electron volt of energy. So we can say that these peaks are in the visible region. The static dielectric constant, which is denoted as epsilon 0 for this material, is found to be 4.151. Okay, it is the onset value of epsilon 1. Refractive index is found to be 2.037. It is again onset value of an omega. Threshold energy for epsilon 2 omega is found at 1.6 electron volt. That pronounces the optical band gap of CS2AgSbBr6, which is very near to the estimated band gap of these compounds. Optical conductivity is defined as the conduction of photoelectron in the presence of electromagnetic radiation. This CS2AgSbBr6, it starts to increase after 2 electron volt. So the absorption coefficient of the compound presents about the fraction of incident electromagnetic radiation absorbed by unit thickness of that compound. More is the absorption coefficient, it means more is the efficiency of the compound to send the electrons from their valence band to conduction band. It has been found almost negligible till 2.2 electron volt for this material, means till the 2.2 electron volt of energy, no transition, almost no transition will take place from valence band to conduction band. So optical conductivity and absorption coefficient spectra reveal excellent light harvesting efficiency. Reflectivity and energy loss spectra confirm the material's low reflectance and minimal energy dissipation in the visible range. The optical response suggests its suitability for solar and photodetector applications in visible and near UV region. This curve you are seeing here is the variation of thermoelectric parameters with chemical potential. In figure A, we have plotted for Seebeck coefficient. Figure B is plotted for electrical conductivity. Figure C is for power factor. D is for thermal conductivity, which is contributed by electrons only. And E curve is for the figure of merit of these materials. So the magnitude of S decreases slightly with temperature due to increased carrier excitations. Conductivity increases with temperature, which shows thermally activated carriers. It suggests strong electronic transport pathways away from the Fermi energy. Power factor is enhanced at 900 Kelvin. You can see that the highest peak is for red color in power factor, and this red curve is represented the temperature 900 Kelvin. So we can see power factor is highest for higher temperatures. Which shows improved thermoelectric performance at higher temperatures, right? So reflects a strong correlation between Seebeck coefficient and electrical conductivity. Electronic thermal conductivity increases with both temperature and energy deviation from Fermi energy. As you can see that as temperature increases, the electrical conductivity increases, right? It is highest for red line, means at 900 Kelvin, and is lowest for lower temperatures like purple line showing for 300 Kelvin. Indicates stronger electronic contribution to heat transport at high temperatures and optimization required to reduce this lattice thermal conductivity for better ZT. Figure of merit exhibits symmetrical peaks near plus minus 1 electron volt, as can be seen in the figure E, 6E, right? It indicates efficient carrier regions. It slightly decreases with temperature. As you can see, the red line curve is attaining the lowest height in among the three. near the Fermi level. So it demonstrates that a strong potential for low temperature thermoelectric applications. The study provides a comprehensive first principles insights into CIS2 SBBR6 and demonstrate that the material is structurally and optically stable. It offers promising potential for lead-free, environmentally safe photovoltaic and thermoelectric devices, contributes to the search for sustainable alternatives to toxic lead-based halide perovskites. These are some of the references. So thank you so much. Thank you so much for listening me so carefully. And I am here thankful to provide this uh, valuable uh, opportunity to present my research work on this globally platform. So thank you so much for the Cryogenicist. Thank you.